Good morning, one and all. So, today is a remarkable day for the PG and Research Department of Chemistry, RD Government Arts College, Sivagangai. So, as per the direction given by the Alagappa University, Karaikudi, today we are going to conduct the public viva house examination for Mr. A Balasundaram, a part-time research scholar from our own department. He has carried out his research work under my guidance, and his title is Production of Petrodiesel Equivalent Biofuel from Vegetable Oils. I welcome one and all for participating this public viva house examination, and it will be very useful to hear and to participate, to ask any questions, to clarify your doubts and so on. And this occasion, I welcome Dr. Mohanbhai N. Patel, an external examiner from Gujarat, and he is a professor in Department of Chemistry, Sardar Patel University, Gujarat, and he is a MSc, MPhil, PhD, and he got PhD from Gujarat University at the year of 1989. He got a wide, rich experience in the academic field, and his research interest is bioinorganic chemistry, and coordination polymers. He is expertised in bioinorganic chemistry, and he got many awards from various reputed institutions. And so far, he has published more than 82 papers, most of the papers from international journals, peer-reviewed publications. He got many research projects from various funding agencies like UGC and Sri G Chemicals and Merti Tech and etc. Approximately in the quantum of about some 25 lakhs to 30 lakhs rupees he got it in various funding agency. So such a personality has been appointed as the expert examiner for the today's public viva house examination. So on behalf of our department, there is PG and Research Department of Chemistry, I welcome Dr. M. Patel to conduct this public viva house examination. And the rest of the session will be handled to Dr. M. N. Patel. Sir, Professor Sir, you please go ahead.
So thank you very much, Dr. Singh, for your nice introductions. So straightforward, I suggest candidate to present his work. So Balasundar, you may present your work.
Good morning to all. Let me present my thesis. Good morning again. There is a delay. I'm sorry for that. Um, I am here to defend my thesis on production of diesel equivalent biofuel from vegetable oils, and this was guided by Dr. Cyril, head PG Research, Department of Chemistry, and the research scholar is myself, Balasundaram, Assistant Professor, Department of Chemistry, APSA College. This was my broad objective when I started my research, and it was production of biodiesel by an innovative route, so that we'll be able to achieve a better yield and than the existing process which is now operating, and it should be more cost effective, and it should be an environment friendly, and a single process which can handle any type of feedstocks, that is, which may contain water content or free fatty acids that can be converted into biodiesel. And before we actually go into the detailed work, let me give some introduction about this biodiesel, and let me tell you what is this diesel is, how chemically or molecular structure of diesel looks like. Here you can see that this is a crude oil fraction. This diesel is a hydrocarbon chain ranging from C16 to C20, and this here can see on the cetane. This is cetane, and this is the basis of diesel. It starts from C16 and ends up to C20, and these are the molecular structure, a pure hydrocarbon, and this is what we use in our compression ignition, that is the diesel engines. It has a flash point of 130 degrees centigrade and boiling point of 270 degrees centigrade. And these are the properties of diesel. For any fuel to be used in a diesel engine or a compression ignition engine, we need to have a density that is around 0.85 grams per ml, around 40 degrees centigrade, and the kinematic viscosity should be between 1.9 to 6, and the city number should be between 40 to 55, and the other flash point is given in the table you can see. And this is the first diesel engine by Rudolf Diesel in 1890. This engine was run using a peanut oil, and raw peanut oil was used as a fuel. In 1890, he invented this first diesel engine. And let me tell you something about the working mechanism. So this is a single cylinder engine. We have a piston, we have two valves, and we have an injector here. And this is through this injector we feed this diesel inside. And this works on 4 strokes: suction stroke, compression stroke, power stroke, and exhaust stroke. And in the suction stroke, you can see that this valve is opening and air is let inside this cylinder, and that is what we call the suction stroke. And lot of air is drawn into the cylinder. And at the end of the suction stroke, the valve is closed, and then this piston is moving upwards. Okay, so it is compression stroke. So it compresses the air to 1/15 of its original volume, so that the temperature of this air reaches around 500 degrees centigrade, and the pressure is about 15.2 atmosphere. And at the end of the compression stroke, this diesel is injected through this injector at high pressure. So once this diesel is injected into this, combustion takes place in the combustion chamber, and it explodes violently and produces a pressure about 100 atmosphere and a temperature about 1500 degrees centigrade. And because of this huge pressure, this piston is moved downwards. So this is the to and fro motion that is causing the piston move and make a cyclic rotation. And at the end of the power stroke, all this diesel would be converted into carbon dioxide and water, and it will be ejected out of this exhaust valve. So this is how this diesel engine functions. And normally we have to understand the mechanism of how this diesel is getting combusted. So kinematic viscosity is very important when we feed this fuel through this injector. And if the viscosity is very high, this injection pattern can be affected, and the whole process can get collapsed. And for any alternative fuel to be used in a diesel engine, it should be an hydrocarbon and should have a viscosity between 1.9 to 6, and flash point between 60 to 230 degrees centigrade, and CT number, and so on. And initially this raw vegetable oil was used in this diesel engine, and later on, due to this low cost crude oil fractions, that is what we get from this crude oil, that is the petrodiesel, replaced this vegetable oils. And from almost 1900 or entire 1900, we were using this petro crude. And this is the chemical structure of the vegetable oil. And this chemical structure, you can see that it contains a long hydrocarbon fatty acid group. and this is the based on this glycerol backbone. So this is the actual vegetable oil, and these three fatty acids may differ in structure. You can see that they have different structures. And the triglyceride means we have this triesters. We have three glyceride groups, so that is why it's called triglycerides. And this triglyceride and makes is made up of glycerol and three fatty acid component. And uh, the different oils which I have considered for the present work are the sunflower oil, palm oil, neem oil, jatropha oil, and neem oil. These two oil are edible oils. You can see that here. This sunflower oil and palm oil are edible oils, and these two are non-edible oils. And these edible oil, after being used for cooking, this is a waste. So this can be converted to biodiesel by this process. And these three are non-edible oils. And let me tell you something about this chemical composition of this sunflower oil. This is made up of, you can see that sunflower oil is made up of, major portion is linoleic acid. So you can have the C18, the two double bonds in this linoleic acid. You can see the structure of this sunflower oil. There is a fatty acid of the sunflower oil. And this palm oil, it's having a major component of palmitic acid. So that is why it is called palm oil. Palmitic acid is 44% and the oleic acid is 39%. And neem oil is made up of, the major portion is oleic acid. So depending upon what type of acid, fatty acid we have, their kinematic viscosity differs, their density differs, and hence the actual quality of this biodiesel. And this is jatropha oil, where we have an oleic acid and the linoleic acid in almost around 40%. And this is fungi oil, have a wide spread of composition. The major is oleic acid, and next to that is linoleic acid. Okay, so let me tell you what is biodiesel actually. So biodiesel is nothing but alkyl esters of fatty acid. So this is the alkyl ester, and this is the methyl ester of fatty acid. This is the fatty acid group. So this is the target molecule. For any molecule which has this structure is called a biodiesel. And if you see what is the difference between biodiesel and petrodiesel, this is biodiesel and this is petrodiesel at the bottom. Here have the similar structure of hydrocarbons, both below and above, but the only thing difference is this ester function group. We have this in addition to this petrodiesel. So this is what makes different from this petrodiesel. And India's need for a diesel is likely to touch 8 million tons. So 8 million tons of diesel is needed every year for India. I will tell you why I'm mentioning this slide a little later. And diesel said in 1912 that use of this plant oils, that is this vegetable oils, may be insignificant today, but in course of time it gains importance due to this pollution problems and other problems. This biodiesel is gaining some importance now. And this was the first patented process. This is called alcoholysis. And this first patent was done by the University of Belgium in 1937. And that is this is the first production of alkyl esters of fatty acids. And later on, we can see that in 1940s there are some other patents coming up for the production of alkyl esters of fatty acid. The target molecule was alkyl esters of fatty acid. That is called biodiesel. And a lot of patents were there in 1940s also. So this is the reaction that is leading to biodiesel. You can see that this is the triglyceride or vegetable oil. What you have here, we have methanol. Methanol is being reacted in the presence of a catalyst called sodium hydroxide. So this sodium hydroxide dissolved in methanol will react with this triglyceride to give this glycerol and mixed esters of this fatty acids. So these are individual components. So it has been broken into three components. So and therefore the viscosity will drop down by some 7 to 8 fold, and then it can be used inside current diesel engines. And let me tell you what are the types of process that is available currently. So currently it started with the base catalyst transesterification was the first process in 1937. And then they came this acid catalyst as transesterification, and we have enzyme catalyst transesterification. All are transesterification process. The only difference is we have the catalyst is different. This is a base catalyst, maybe sodium hydroxide, acid catalyst, some sulfonic acids, and some enzymes, biocatalysts are being used for transesterification. And that's a supercritical transesterification. The supercritical transesterification is nothing but reacting this vegetable oil triglyceride and methanol at very high temperature and pressure. So without any catalyst, so it is getting converted instantly into glycerol and methyl ester, but it's a high pressure process. It requires a very high temperature and pressure, and that's why it is not desirable. And lately, this acid and alkali catalyzed two-step transesterification process is being now investigated more by researchers. So this was the 5 major types of process being used, and I will tell you one by one what are the disadvantages of this process. So this base catalyst is the most preferred process because it is very fast, and but there is a loss of yield of this biodiesel due to soap formation. Okay, so this acid catalyst transesterification is very slow, and it takes a lot of time to get the final product. This is an instantaneous process. I can get this transesterification done in within 2 or 3 hours, but the problem is separation of soap makes it more complex. And enzyme catalyst transesterification is very costly, and this is also a fast process, but this supercritical transesterification needs high temperature and pressure. And this acid and alkali catalyst two-step, they have combined this two-step. I'll tell you why these two steps have been combined. Because for the raw vegetable, we does not have free fatty acid, there is no problem. But if any vegetable oil which need to be converted into biodiesel is having a water content and this free fatty acid, it can hinder the process. And these are the supercritical process, and this enzymatic lipase is being used for this transesterification. And all the processes are there, but it's most expensive. It is not the processing will take up the consume most of the cost than the raw material. And we can compare this different types of process. We can have this homogeneous alkaline catalyst, sodium hydroxide, and this heterogeneous catalyst, alkaline catalyst, homogeneous acid, homogeneous heterogeneous acid, and enzyme catalyst. When you compare all this different types of catalyst reaction, this homogeneous predominates. We can see that this base catalyst predominates, and because it's very user friendly and it can get the product in very short period of time. But the only thing disadvantage is that soap formation is there, and sometimes if the free fatty acid is high in this free fatty acid content, it may form an emulsion, and it will be very difficult to separate the biodiesel from glycerol. And then so this base catalyst is being widely used for production of biodiesel currently. Okay, so even though there is a loss of yield due to this free fatty acid, this is being used because it's the most economical of the available process. Of all the 5 processes, this is the most economical process, and it requires only low temperature and pressure. And but the starting material or the raw vegetable oil should be low in moisture and free fatty acid. That is the only problem we have this type of base catalyst process. But if you use an acid catalyst, it may be a much time-consuming process. And so this process for triglycerides containing when you have high FFA and containing raw material, and the process that is being employed is base catalyst, but it will result in soap formation, and because of the soap formation, the yield will be decreasing, and it requires to washing of biodiesel is necessary. So we have to wash the biodiesel at least 7 to 8 times to get pure biodiesel, and therefore leading to a lot of effluent discharge. So it is not environmental friendly, and so it increases the process time and energy consumption. Though acid catalyst would solve the problem of soap formation, the process much slower. It takes very long time, and sometimes the temperature need to be increased for this type of acid catalyst reactions. And I need to tell you something about feedstock for biodiesel, because we convert all the vegetable oil into biodiesel, and it can compete with food materials, food stocks. Okay, so the raw material should be an used vegetable oil and or non-edible oil. I was careful on that because my research would have some impact on the society, and therefore I selected this used vegetable oil and non-edible oil for this conversion of it to biodiesel. And the answer is that we use it for food, and then we can convert it into fuel. So we use lot of cooking oil, and there is a lot of waste from soap industry. And if we can increase the area of vegetable oil production, that can be a new source of raw material for biodiesel production. So once this is used fried oil, after some time it gains lot of releases lot of free fatty acid, and it is not fit for consumption. And so this used filtered cooking oil can be recycled and converted into biodiesel. And India produces around 9.2 million tons of waste cooking oil every year, which is the highest in the world. So we consume a lot of vegetable oils, and we produce 9.2 million tons of this waste cooking oil, and we can import this cooking oil from US at a cost of 20 per liter. And but where does this the used vegetable oil go? I will tell you. And so this 8 million tons is required for India. So if we can convert this 9.2 million tons of waste cooking oil into biodiesel, we can very easily meet our yearly demand of diesel, and there is no need to import diesel from foreign countries. That will save a lot of money for our country. And this where does this used vegetable oil go is that it is used again and again, okay, in the food industry, and this causes serious health problems. So you can never see that this oil is being discarded. It is used again and again in the food industry, and people are not aware of this, and therefore a lot of health problems are being created. And therefore I wrote an article in June 2019. This was about India's 2030 automotive energy scenario. We know that India is moving towards electric vehicles by all electric vehicles by 2030. And India's over-ambitious target was that all these electric vehicles should be, all the current model vehicles which are running on this should be running on electric vehicles. But this is a over-ambitious plan, because country like India, we don't very easily switch over to this type of technology, electric vehicles. So, in this article, I have given some policy recommendations to the government. That was in June 2019, and there are some policies which I can show you. The government of India should bring a policy to ban the reuse of used vegetable oil containing more than 25% of free fatty acid, and allow the import of used vegetable oil and fatty acid oil for biodiesel conversion. And the policy for collecting used vegetable oil from bulk users such as food industry, and mechanism in place to convert used vegetable oil into biodiesel in a decentralized manner. And the policy for creating health awareness on the consumption of used vegetable oil and benefits for converting them into biodiesel. These were the policy recommendations which I was giving. And later on, you can see that by August 2019, there are news coming up that state-run oil marketing companies to buy biodiesel for making from used cooking oil, and all this thing is happening now. And you can see that the government is taking initiative to convert all this used cooking oil into biodiesel and cut imports. And now we can see it has gained some momentum. There is a lot of awareness among this usage of reused cooking oil, and everywhere you can see that collection points are available now, and it is being sent to every hotels. You can go and see they have some complaint certificate that this dining hall is using ROCO, that is repurposed using used cooking oil, and this is gaining some momentum. So that was my objective of my research. So if we can develop a process, already the process are there, but if we can develop a process which is still more economical and easy to convert all this used vegetable oil into biodiesel, that will be a wonderful idea. So that was my objective. It should be that process that has to be developed is that can convert any used vegetable oil or vegetable oil which contains lot of free fatty acids into biodiesel, and it should be economical both in material and energy wise, and it should be efficient, environmental friendly, and do not involve high temperature and pressure, and it should be capable of producing biodiesel from any vegetable oil. Okay, so irrespective of the amount of free fatty acid content. And so the current process, that is base catalyst transestivation process, if we try to use this for conversion of biodiesel, there will be a lot of soap formation, because used cooking oil will generate a lot of free fatty acids, and this free fatty acid along with the moisture content will result in soap formations, and sometimes emulsion formation will be there, which will make the process more complex, and the biodiesel separation may not be there. Okay, so this soap formation is decreases the yield of that total process. So what the amount of free fatty acid that is present in the used cooking oil will be converted into soap. So that is not available to be converted into biodiesel, and this has to be washed, and that requires a lot of water washing, and it leads to effluent discharge and have a lot of environmental impact. And this increases the process time and energy consumption of this process. And most of the researchers, they were trying to solve this problem, and the fifth process is that they were switching over to acid and alkali catalyzed two-step process. That is, first they will esterify the free fatty acid and then go for alkali catalyzed transesterification process. That was the two-step process. They combined this acid catalyst and the alkali catalyst process, and even though that process has given some results but not better results, soap formation has decreased, but cannot completely eliminate the soap formation, and the process is also taking much longer time, and there is also a possibility of corrosion in the engines because of this acid catalyst process. And when I go through this literature review of this two-step process, there were a lot of work. They were changing this catalyst, that catalyst, and all this thing, acid catalyst, and so on. But still, this process suffers from a lot of disadvantages. The soap formation and other disadvantages are still there, but it has been decreased to a certain extent, but not to an extent where it is completely eliminated. And you can see that this is biodiesel that is containing soap, and this is a clear biodiesel. So if we want to convert this into this pure biodiesel, we have to wash it at least 7 to 10 times, and it takes a lot of water and time, and it may take sometimes it may take several days or even weeks to fully separate this biodiesel. So it's more time consuming. There's already existing trans-esterification process by alkali base. And my work were focused on the problem of soap formation. Okay, I want to eliminate this washing step. So once I can eliminate this washing step, then I can decrease the process time to a considerable extent. So it is not done so far. By any of the process, it is not achieved. And I want to do this, which can significantly improve the time and cost involved and improve the yield of the biodiesel. Not only it saves the time, but also improve the yield, because no soap is formed, then 100% can be converted into biodiesel. That was my main idea. So convert the soap into free fatty acid, but as such cannot convert this free soap that is present in the biodiesel to be converted into free fatty acid and then esterify. That is not possible because it forms an emulsion. And if we can convert the soap into biodiesel, then we are going to get 100% yield. That was my main motive behind this research. And I'll tell you the new process which I have designed for this. And this process is containing 3 steps. And first is the saponification process. Soap was the problem for achieving this 100% yield. So what I did was that I converted everything into soap. Here you can see that the whole oil I have converted into soap. Okay, it's not shocking. And this was done within 5 to 6 minutes in the ratio. If I take this vegetable oil and this sodium hydroxide in the ratio 1:3, and this takes place at 60 to 70 degrees centigrade. Okay, and then if I stir it with a mechanical stirrer, I can convert this entire thing into soap. Okay, and this soap, once produced, we can see that if it is an used vegetable oil, it will have triglycerides and it will also have free fatty acid. So now I have converted these 2 components that is present in the used cooking oil. That is both this triglyceride and this free fatty acid. I have reacted with sodium hydroxide and I have converted all of them into soap. That is sodium salt of fatty acid is called soap, and glycerol. So I have converted everything into soap. All this free fatty acid that is present, and also the triglyceride. So we don't need to worry about the amount of free fatty acid because everything is going to get converted into soap. Okay, so once I convert this into soap, my second step is that just I will react this with concentrated 6 molar sulfuric acid with constant stirring, and once I mix this concentrated sulfuric acid you can see that it beautifully separates into 4 layers. So liberation of free fatty acid was the target and the second step. So once I add the sulfuric acid, you can see in this equation, once I add a sulfuric acid to this sodium salt of fatty acid, I convert this sodium salt of fatty acid into free fatty acid and sodium sulfate. So this is what happened when I just mix this with 6 molar sulfuric acid. Based on the density gets settled down. So being dense, the solid sodium sulfate settles down, and then a layer of water, and then glycerol, and then free fatty acid. Now I can take this free fatty acid out of it using a separating funnel. So this was the 4 layers which I was getting, and now I can remove this top layer by separating funnel, and then I can go for the third step. Okay? So the third step is nothing but simple esterification process. So this is the process where I am not going to follow trans-esterification. It's a new process where the earlier process where trans-esterification process. This new process, the only process where I go for esterification. So esterification of this fatty acid which I have obtained from this second step. So this free fatty acid, which is the end of the second step, I can remove this and I can add this the excess of ethanol or methanol with the presence of small amount of sulfuric acid. So this is needed to act as a catalyst. And if I stirred it for 1 hour, this results in the formation of 2 layers. This water layer may not be visible, and this is what I'm doing in the third step. You can see that this free fatty acid reacts with ethanol in the presence of sulfuric acid, and then it is converted into this target molecule biodiesel ethyl esters of fatty acid and water. So the only problem is I have some water. What I can do is that I can remove this water by evaporating. Okay, so this is also an equilibrium reaction. So if I have to remove the water by heating, then I can shift the equilibrium to this right side. And the whole process I can show you in this flow chart. This is filtered used vegetable oil, and I add sodium hydroxide, convert this into soap, and once it is converted into soap, I add acid, that is sulfuric acid. Once I add the sulfuric acid, it separates into 4 layers, and the top layer is separated and then mixed with the alcohol, ethanol or methanol of sulfuric acid, where it forms biodiesel, and this biodiesel can be removed. So this is the simple process which I have devised, and I have confirmed it with the, though this is not necessary, some scientific confirmation is always essential. So I did this confirmation by studying the FDR spectra and the GC mass spectra, and this is for used vegetable oil, where we have this ester CO stretching at 1750 and peak 1 at 3471, produced by the CO group of the esters, and CH stretching of long alkyl chains at peak 3 and 4, that is around 2925. And you can see this absorbance at 3400 to 3100 because of the ester group. And this second spectra is for free fatty acid. So the second step, the product I got, I just took the FTI spectra of this, and at 17 times, this is due to the CO stretching of the carboxylic acid group. So it shows that that the triglyceride has been converted into free fatty acid, and around 300 also I get this carboxylic CH stretching, OH stretching is also there, and alkyl stretching also there. So we can confirm this, that this triglyceride has been converted into free fatty acid. And after conversion to biodiesel by reacting with the ethanol, I have this spectra 3 for biodiesel, which again shows that 1750 there is an ester group. So I can confirm that ester has been formed, and that is with the help of this FTR spectra. And also I confirm this with the GC mass spectra of biodiesel. And these are the properties I measured for this biodiesel: density, kinematic viscosity, and I compared this with the ASTM standards for biodiesel, and all are found to be having this same within the range. So this kinematic viscosity is around 5.7 for this sunflower vegetable oil, and the acid number is also slightly above, because we were using this acid catalyst esterification. That is so because of that there is some increase in this acidity. And this is the instrument, digital viscometer, that I have used for measuring this viscosities of both this raw vegetable oil and the product biodiesel. And it's a very simple machine, just as the latest machine, which is just we can immerse this machine into the oil for which we have to measure this kinematic viscosity. After a very some 30 seconds, it can give you the display of this kinematic viscosity. Very simple method. And the special feature of this process, if you see that this process has given a very good yield, almost 99.9% I have got in less process time, and the steps involved are very simple. There's a low temperature, low pressure, so it can be done in an open vessel. There is no need for any reaction vessel. That can be done in any open vessel, and it does not involve any toxic materials. We use ethanol, and there is no effluent discharge at all. There is no washing process, and therefore the effluent discharge is completely eliminated. And this is fast and more economical than all the other four or five processes which we have earlier. And the byproduct can be used for other applications. Sodium sulfate and glycerol can be used for various other applications. And this process does not require high temperature and pressure. And this biodiesel can be produced from any oil, that is vegetable oil. If it is not even in used vegetable oil, if it is a non-edible oil and it has higher content of free fatty acid, again we can use this process to convert this into biodiesel. And it can be done in small batches. Even if we have in home itself, we can use this process if we have a small design of this reactor. And that is what I have done. So added one more to the list. So earlier there were different types of process that can give you biodiesel, and this sixth one I have named it as a SAFAIL. That is because from the name, saponification, fatty acid liberation, and esterification, the three steps I have combined it and named this process as SAFAIL process. And there will be a sixth process hereafter for production of biodiesel, and I have named it as SAFAIL process. And I have applied this SAFAIL process to neem oil also. So then in this neem oil, you can see the lot of is a non-edible oil, but it is used as a medicine. So it has 30 to 60% of content, oil content is there. And India produces about 30,000 tons of neem oil every year. So it's a potential raw material, but it is used in organic farming also. So this azadirachtin, that is the chemical content that is present in the neem oil, is responsible for this insecticide characteristics and all. So once this azadirachtin is removed from this neem oil, this oil can be converted to biodiesel, and then it can can run vehicles. So this neem oil were containing 21% of free fatty acid. So even though it is having a 21% of free fatty acid, that is no problem for this type of process, that is the SAFAIL process. And I have estimated this raw neem oil through this GC mass spectra and confirmed this its content. And then this FTA spectra for raw neem oil, and that is just this triglycerides. And I applied the same process, just I changed this used vegetable oil, and I am having this neem oil. It is heated to 60 to 70 degrees, same type of process, and it's very easily getting converted into biodiesel. And these are the properties which I have for this biodiesel, neem oil biodiesel, and all are found to have this satisfy this ASTM standards, or all are well within the ASTM standards. And these are the FTA spectra of neem FFA and its biodiesel for free fatty acid. And then you can see that this point, where this is the point at that is 1710, you can have a change. So from free fatty acid to ester. So this implies there is a conversion of neem oil fatty acid to neem oil biodiesel. And so neem oil, lot of people have worked on neem oil esterification. Here I have compared the different types of process: trans esterification process and two-step process, and two-steps esterification and trans esterification process. And there are several types of process. Here you can see that this process, the present work, is giving you 99% yield. And other than this, trans esterification gives 95%. This may be due to the presence of low amount of FA in neem oil, because different area has different amount of neem oil content, FFA content in the neem oil. And this is the comparison. So this is the present work which is done, which is giving you 99% of yield. And this is the time taken almost less than 1 hour. It takes only 1 hour to convert this used vegetable oil or any oil into biodiesel very easily. So this I have published in this journal, International Journal on Emerging Technologies. And another thing is applied the same subtle method to palm oil. You know that India imports a lot of palm oil from Malaysia, Indonesia, more than 8.3 million tons to India annually. And once this palm oil is being used again and again, you can see that there is a considerable improvement, increase in the amount of free fatty acids. So with the day by day, the amount of frying being done, this free fatty acid can increase substantially. Okay, so this used palm oil I have has a lot of potential. You can see in all the restaurants they will be using this palm oil. So this is a suitable process to convert this used palm oil into biodiesel. And the free fatty acid which I was using to convert this into biodiesel was around 12%. And this is the used palm oil using a GC mass spectra convert. Just found out this composition of all this different types of fatty acids that is present. And this is the FTA spectra of used palm oil. And again, it shows the triglycer esters. And the same process applied to this, subtle process applied to this type of conversion of biodiesel. Again, I can got this process done in 1 hour itself, and the yield was 99% when I calculated it. And so these were the physical properties which I got for this used palm oil biodiesel. And the density was around 0.86, and kinematic viscosity was slightly about near this 6, that is 5.7, and but it is within the range. So this is the FTR spectra of FFP and biodiesel of used palm oil. You can see that again there is a change at this point from free fatty acid to ester, that is biodiesel. And this work has also been published in this journal. And Jatrop oil, you know that this was promoted much earlier for it's called a biodiesel plant that can give you biodiesel. And also I have converted this biodiesel Jatropa into biodiesel using the same subtle process, and the properties which I got is also well within the ASTM standards of biodiesel. And these are the actual Pongima oil. This is a Pongima oil and biodiesel converted into pure biodiesel. This Pongima oil has an oil content of 32 to 42%, and again I can produce 99% yield of Pongima oil. And these are the properties which I got for this Pongima oil biodiesel. Again, well within this, just density slightly above, and because of the various components present in this oils. And after that, after preparing all these oils, I was using all this oil to test the engine performance. So that was one of the most important step for my research. So I used this type of test rig, and this is the engine which I was using. It's a VCR engine, and this is it's a stationary engine. So we can it's a multi-fuel engine. I can supply this fuel, and dense can also be supplied, and data can be acquired and then stored in a computer, and then later on it can be analyzed. And this is a 4-stroke water-cooled engine. It has an RPM of 1500, and this is the data acquisition system and gas analyzer. I want to test the performance as well as emission characteristics. And the parameters which I want to analyze was this brake thermal efficiency. That is, the thermal efficiency is the amount of fuel supplied, and what is the amount of work being done is called brake thermal efficiency. And brake specific fuel consumption is also being done. And on the emission parameters, I was exhaust gas temperature was also measured. And in the emission parameters, we have tested for hydrocarbon, carbon monoxide, carbon dioxide, and oxides of nitrogen. These were the parameters which I have analyzed. And I did a blend of pure diesel, biodiesel, the sunflower oil biodiesel. So this I have done for all the 5 oils. And this sunflower oil is mixed in 20%, is called 20 BD. So it means that we have 20% biodiesel and 80% normal petrodiesel. And this is 40%, that is called 40 BD, 60 BD, and 80 BD. There's 80% biodiesel and 20% diesel. And also I have included this biodiesel, which is made entirely by the supple method, which is the new method, and the traditional method, that is homogeneous base transfiguration method. I have named it as FSFBD. And this process, I can yes, this brake thermal efficiency. This is the brake thermal efficiency for sunflower oil biodiesel. Here, this color, there is violet and blue. Both are for biodiesel, pure biodiesel, and this black is for pure petrodiesel. And these red, indigo, and all this purple, green are for blender. These are represented by this percentages 20, 40, 60, and 80. And here you can see that at different loads I have tested this brake thermal efficiency. That load is 25%, 50%, 75%, and 100%. Okay, so depending upon the load, this characteristics may change. That is that the thermal efficiency may change. So at 100% load, you can see that is a 1.95% higher. Efficiency is higher for this biodiesel. And for 25% load is 1.35 and 20% biodiesel. And so you can see that both this biodiesel produced by subfill method as well as this HBT method is found to be similar. Slightly, subfill method is slightly higher. Okay, maybe the advantage may be because of the absence of soap. So this biodiesel, I have not washed it. So soap will be present in it. I want to test it by the HBT method and subfill method so that I can make a difference. But there is only a slight difference I can notice between these two methods. The rest, all the other parameters are similar. So for brake thermal efficiency and for brake specific fuel consumption, and just it will be just opposite to that. So efficiency, if efficiency is good, consumption will be low. So you can see that there are all the points. There is both the biodiesel, 100% biodiesel method almost similar. And the exhaust gas temperature as expected, this you can see that 100% diesel is having an the temperature is very high. Okay, and compared to biodiesel, all this 100 pure biodiesel, the flame temperature is very high because the energy density of petrodiesel is high. Therefore, the exhaust gas temperature must be high, and this is always found to be true. And hydrocarbon emission, you can see that this emission of hydrocarbon is found to decrease with the addition of biodiesel. So as we go on from 20, 40, 80, you can see that hydrocarbon emission decreases. Okay, so this is black one is for pure petrodiesel, and at all loads you can see that there is a decrease in hydrocarbon emission. And for carbon monoxide, you can see that again this with the addition of biodiesel, you can see that this goes on decreasing. So carbon monoxide emission is high for pure diesel, petrodiesel, and for other diesel it is almost decreasing, and for same for this 100% biodiesel it is very almost the same. And carbon dioxide emissions, only the carbon dioxide emission, you can see that this biodiesel gives a high amount of carbon dioxide. The difference was very small, and the difference between subfill method and HBTM method is almost similar. You can see that. And oxides of nitrogen was also high when we use a lot of biodiesel. So that is because of the high flame temperature. No, a peak flame temperature inside the biodiesel, the energy density was higher, the CT number was higher. Therefore, at the high flame temperature, there's a possibility of oxides of nitrogen formation. That was found to be true. And this the similar thing I have done it with the use palm oil, and it obtained the same result. And for emission parameters also, and the brake thermal efficiency was only 1.04% higher than that of the pure diesel. And this is for neem oil biodiesel, same procedure I have carried out, and the result was coinciding with this data available, emission parameters. And this is for Jadrop oil. Jadrop oil I have done for the similar emission performance and emission testing, and the efficiency was 1.75% higher compared to this petrodiesel at 100% load. And these were the observation I have made out of all this engine performance testing. There is a brake thermal efficiency and brake specific fuel consumption, exhaust gas temperature, and all this emission parameters were almost the same for both the biodiesels, the subfill method and the HBT method. So there's no very large difference. Some advantages found to be in subfill method. Okay, so they're slightly better. It was slightly, but not much. Slightly better. This may be due to the presence of soap in this method. So in this method contains soap, so that fuel consumption may be hindered by this presence of soap, and that is what I think this advantage will be between the subfill method and the HBT method. And these are the conclusions and features scope of study. The conclusion is that the vegetable oil, both edible and non-edible, can be converted into biodiesel successfully, and vegetable oil containing any percentage of FFA can be converted into biodiesel with without loss of any raw material. This process gives good yield, almost 99% for any vegetable oils, less processing time and does not involve any skilled manpower. And the conclusion, these are the conclusion that it does not involve any toxic material, without effluent discharge, fast and more economical. These byproducts can be used for various application, and the process does not require high temperature. It can be done in an open vessel. That is the most advantages of all the other methods. And so effluent soap formation is not there. So future scope is that this production can, this method, same fill method can be applied for this rubber seed oil, cotton seed oil, soybean oil, peanut oil, and all the other, even animal waste, and all the other things. It can be in future study is possible based on this fill method. And optimization of the process of the saponification process can be done. And reusing of sodium sulfate as a byproduct in the saponification process can also be tried. These are the future scope of this research. And thank you one and all. And I thank all the people who have supported in my research work and making this possible. Thank you.
Professor?
Yes. So nice presentations and very good piece of work and very applicable work. Your work will solve the problem of the oil. So now the session is open for the discussions. Anyone can ask the questions from the audience.
Good morning, sir. Very nice. Let me ask a question. Shall I ask one question?
Thank you, sir. Thank you, sir.
What is the expectation on government of India, especially for the advance all the vehicles by 2030? What is your expectation?
India's target was going all electric vehicle by 2030, and I think that this is far from reality. Because only in developed countries this is catching up. Electric vehicles are catching up, and there is a possibility for going all electric after 20 years. So first, India has to use the potential that is available in used cooking oil, and after that, maybe after 20 years, this is possible. And India can very easily use this used cooking oil, convert this into biodiesel, and satisfy its diesel demand. And this target of achieving all electric by 2030 may not be a reality, I think. Thank you, sir.
Hello, this is Pumalai from Japan. Thank you, sir. I think you're presenting very good one.
Any other questions, sir?
Hello.
Yes.
Yes, this is Pumalai from Japan, Toyota. So thank you for presenting everything. I think it's very nice to hear everything. Just I want to have some questions. I think it's for, actually I'm working in the aircraft industry. So I think it's a Boeing, the world biggest airplane maker. The Boeing will be trying to use biodiesel from, especially biofuel, from 2030 onwards. So what is your expectation? Because you are showing that it's you're going to import from US 20 rupees per liter, something like. So do you it's feasible in India to make it everything?
Yes, actually, right now India has a ban on importing this used cooking oil from United States and other countries, and it is available at very cheaper cost. But because US is producing a lot of used vegetable oil, and it is being smuggled inside the countries and is being used as a food material. So once this is checked, that this used vegetable oil is allowed legally for producing biodiesel, and this oil that is imported illegally from other countries does not mix with food. Once it is being converted into biodiesel, if this is legalized, there is a possibility that the price of diesel can fall less than more than 50%. And it
Oh,
also
thank
can
you.
be used. Oil is also using this for running their jets and all these things. And it is a possibility that already there is some biofuel being tested in Boeing. Thank you.
Okay. Thank you.
Ah, sir, good morning, sir.
Good morning, sir.
Oh, good morning, sir. Sir, your work is very fantastic, very excellent work. But I am asking simple questions. So, in many countries nowadays used for cars, any in batteries, but our country is only used for fuels, petrol, diesels. What's your suggestion? You also your research work for use for biodiesels. So what's your
Yes,
suggestion
yes,
in any method,
yes,
the
yes,
methodology used for your research work, or
yes.
useful for country?
Yes, yes, yes. It's a very good question. My suggestion is that right now, these electric vehicles are very costly. So the first thing that should be employed is only in metro cities where we have a lot of vehicles. If we take Chennai and other metro cities, we have crores and crores of petrol and diesel vehicles running there. So first, this implementation of all electric vehicles should be carried out only in metro cities. In 2030, that can be achieved. So once if that is being done, that is a law is enforced that only battery vehicles can play in metro cities. Lot of pollution problems can be avoided, and there will be a very good opportunity for the biodiesel also. Thank you.
Okay, sir. Okay, sir. Thank you, sir.
Any more questions from the audience? Okay. So you suggest that in your process, the ethyl alcohol are used. Ethyl alcohol is
Yes,
required.
ethyl or
How much
methyl alcohol, both can be used.
quantity of ethyl alcohol is required?
Sir, not clear, sir.
You suggest that in process, ethyl alcohol is required for the saponification, isn't it? But how much quantity of ethyl alcohol is required for the separation?
The third step, sir. Sorry, it's not. Yes, sir.
In process, in process you used ethyl alcohol. So how much quantity
Oh,
is
yes, sir.
required?
That is the third step that you asked.
Ah, yes.
Third step, sir. I said, yeah, excess alcohol is always unreasonable. That is 20 is to 1 ratio of ethanol and this free fatty acid is better. And if that is since this is an equilibrium process, and if you use excess of alcohol, and this equilibrium can be shifted towards the production of biodiesel, and simultaneously we have to remove this water content also. That can be done by heating, but heating should not be done beyond 78 or 80 degrees because the boiling point of ethanol will be is around 78 degrees centigrade. So that will be converted into vapors. So there will be a loss of ethanol alcohol. So at temperature just below 60 or 70, we can go for this. And excess of alcohol is always better, but too much of alcohol will result in a higher cost of production.
Suppose in production of 1 liter of biodiesel, so how much alcohol is required? Plus how much alcohol is
Okay.
required?
Yeah, actually, it's an 1:1. It is a 1:1 is essential, but in order to shift the equilibrium to biodiesel production, I always use 20 liters of this alcohol and 1 liter, but the consumption will be very less because it requires just for converting it free fatty acid to alcohol. It may be around 0.25 only consume. Other alcohols can be removed, and this rest of the alcohol can be used again for the same type of process, recycled again. Only very small amount, maybe around 20, for around 20 to 30 ml of alcohol is enough. That can the loss will be very small, but the loss will, due to vaporization is also there. So we have to have a closed vessel and not decrease this loss.
Now, important question: what will be the cost? Cost is an important factor as far as
Yes,
we
yes,
study
yes, yes.
biodiesel. What
Yes,
will
yes,
be the
yes.
cost?
The cost analysis I have done, and it will be around 20 to 25 rupees per liter. I have not done it exhaustively, but a statistical study I have done. But this process, we are getting a very good yield, and therefore the loss is very small, and the temperature is also very less, and therefore the cost will be around 20 to 25 rupees per liter. And exact calculation has to be done in the future scope. That is also one of the future scope of this study.
But so this extraction or production of biodiesel from plant is easy because the plant are available easily. But my question is how the used oil, because it is very difficult to collect the used water, used oil.
Sir, used to it?
How do you? So used oil is difficult to collect. Are the sources
Yes,
of
yes, yes,
used oil
yes.
very placed?
Yes, yes, sir. Yes, sir. Right now, government has promoted this in each and every hotels. People have been given some certificates, and there is a process for collection of this waste cooking oil. That is, this government will pay them 25 rupees per liter, and get back this used cooking oil. And there is a process going on right now. You can find in almost in some most of the hotels in Tamil Nadu. They are collecting this used cooking oil, and they are supplying to the local municipal corporation, and they will collect it in a bigger way, and then they transport this to oil companies. So that is being right now. That is being done.
But availability of quantity is less. I think it's not much available quantity for the production of biodiesels.
Yes, sir. Each and every city has to do that, sir. Every city there should be a collection point, and this collection, this used cooking oil, when it is reselling, they are given some amount of rupees. They are willing to give back rather than using it again and again.
So this kind of cooking oil is only available from the restaurants only, because from household it is
Yes, sir.
difficult to.
Restaurants and KFCs and all this where we have this frying, lot of frying, and when companies like Lay's and all these things where the frying is being done again and again, these are the points where you can have lot of used cooking oil that can be got for converting this to biodiesel.
So now some questions related to research work. What do you mean by citations, and how many publications you have?
I have totally in this research I have done 3 publications, sir.
In which journal you have published it?
In International Journal of Emerging Technology, sir. That is one, and then in one more in International Journal of Advanced Science and Engineering. All are UGC recognized journals, sir.
So what are the impact factor of these journals?
Impact factor is around one is around 2.3, sir.
It is a Thomson router impact factor or others? Thomson router.
It is not Thomas Reuters, sir. They have a different impact factor, sir.
So Thomson Router Scopus index journal, I suggest to publish. So it will be a good piece of work and very applied work. So it must be published in a Scopus journal, like the published science.
Yes, sir. Yes, sir.
Listed in
Yes, sir.
So it gives the more impact of your work. So do you
Yes,
know
sir.
about H index, I index? What is it?
Yes, sir. Yes, sir. There, sir. I have around 1.2 or 1.3, sir. Google, sir. Google index, sir. Google H index is 1.3. Index.
No, it is not a
1.3, sir.
It is not a. Can you give the definition of H index? What is H index?
Average of citation that is in a particular year, sir.
So H index means number of publications. How many your article is cited in a by other
The journal in a particular year.
and how many? Suppose my H index is 10 means my 10 article is cited 10 times in a different journal. All 10 articles cited 10 times in a different journal. So then and then my H index is 10. Okay. So I congratulate for your good piece of work and I recommend
Sir,
Alagappa University for a Doctor of Philosophy degree. So I can say Dr. Balasundaram now onwards. So congratulations.
Thank you, sir. Thank you very much, sir.
thank you, Professor. Hello.
Yes, sir, you are audible, sir.
Thank you, Professor. One of the examiners have some other questions. Sir, in page number 11,
Yes, sir, go ahead, sir.
so what is the other expectation regarding the order of pKa value in long chain fatty acids like lauric acid, palmitic acid, stearic acid, sir?
Yes, sir. So normally this as the length of the alkyl chain increases, the inductive effect is more, the Spacey effect is more, and normally this stearic acid is having a C18, and this palmitic acid is C16, and the stearic acid is C14, and lauric acid is C12, and because of this,
Okay,
this
sir.
order of
Okay, sir.
yeah.
Sir, another question. What is the author expectation regarding the yield of chemical reaction of the homogeneous and heterogeneous alkali catalyst trans-esterification versus homogeneous and heterogeneous acid catalyst trans-esterification?
Yes, sir. This homogeneous alkali-based catalyst reaction, it has 90% yield, but it cannot be compared as because the temperature variations are there. If we go for a heterogeneous acid catalyst, it can catalyze only around 250 degrees. So if you bring down the temperature to 60 or 70 degrees centigrade, there will not be any yield at all. So the comparison is that at some temperature you have to normalize it, and if we have this alkali-based trans-esterification, this 90% at the 70 degrees centigrade, but this heterogeneous acid catalysis will give you 70% at the same temperature. Here we have to increase the temperature to increase the yield. So the yield is very good for alkali catalyst trans-esterification process.
Okay, sir. Okay, sir. Thank you, sir. Professor, you please go ahead.
So okay, I have finished. So I congratulate candidate for his doctorate degree and recommended Alagappa University for the Doctor of Philosophy in Science. That's it.
Thank you, sir. Thank you. My sincere thanks to Professor Dr. M.N. Patel, who is acting as an external examiner for conducting this Viva House examination for Dr. Balasundaram. And I thank one and all who have participated in the public Viva House examination for Mr. Balasundaram in the title of production of biodiesel equivalent biofuel from vegetable oils. I thank our principal who have give the permission to conduct such a Viva House, and I thank the Vice Chancellor of Alagappa University and the Dean R&D, Research and Development, Dean of Research, Alagappa University, the Registrar, Alagappa University, and the professors from our own department and the various academic institutions. I thank one and all for conducting this public Viva House examination in very smooth way. I thank one and all. Thank you. Thank you.
Thank you.
Thank you. Thank you very much, sir.
So, Gilly.
Okay, sir. This Viva House is going to end, sir.